papers, mostly on the first paper, which was published in a conference last year. And also, I will talk about something from a working paper with my colleague, Emiliano Vardas. So this is the structure of my talks. First, I will review some dimension reduction techniques. Then I will talk about the probabilistic PCA and the self-paced probabilistic PCA. And I also show some numerical results. So why we do dimension reduction? There are many reasons. So there are also some very good theoretical reasons. So here is one. So Stone published a paper in 1982 in Annals of Statistics, and he showed that under some assumption, regularity assumption, so the optimal rate of convergence for non-parametric regression, that is p times differentiable, whereas according to this number, n to the power negative p over 2p plus d, and n is the sample size, and d is the dimensionality of the data, and p is the how many times the function, the regression function differentiable. So this has some very important implications about the dimensionality of the data. So for example, if you want to fit a model, right, non-parametric regression model to a data set with 1,000 data points, and your regression function is twice differentiable, p is equal to, and for example, the data is has 10 variables, 10 dimensions. So when you want to double the dimension, say to 20, so if you want to get the same optimal rate of convergence, then you need to increase sample size to 138,900 something. So the sample size increase exponentially. So that means you need more data in order to get a same optimal rate of convergence. So this optimal rate of convergence is defined very technically. So if you want to see the detail, you can go back to the original paper. So this gives us some good reason, right, to do dimension reduction. So another reason is, so in high dimension space, so the half diagonal of a hypercube is nearly orthogonal to all coordinate axes. So this is how we calculate the angle, right, between the half diagonal. So consider this hypercube, so -1. So all the coordinates are -1 or 1, okay, in this d-dimensional space. So the half diagonal can be represented by this vector, right? Any coordinate axis can be represented by this vector. So just one component is 1, all components are 0, all other components are 0. So if you calculate the angle, so it is 1 over the square root of d. So when d increases, right, very large, so this approaches 0. That means theta I approaches 90 degrees, right? That's orthogonal. So based on this observation, so we can see that it is misleading to visualize high dimensional data just by plotting two coordinates of that data, right? So I see the reason. So Beers in his 1999 paper, they point out that dimension reduction is usually applied when if you want to apply KNN algorithm, because the nearest neighbor does not make much sense in high dimension space. So in very high dimension space, so all the distance look similar. So you cannot differentiate whether a point is a neighbor of another point. So based on all these reasons, people have developed many dimension reduction techniques. So the literature on dimension reduction is very vast. So you can think of dimension reduction. So if you look at the data as a table, right, you have each row is an observation, right? Each column is a variable. So usually when we think about dimension reduction, we think about it reduce the number of columns, right? But dimension reduction can also think about it reduce the number of rows. So if we think in that way, dimension reduction also included data clustering, right? Data clustering, we group the rows, right, observations into groups, right? That essentially reduces the dimension. So suppose you have say 10,000 data points, right, rows, right? You divided this data set into say 10 clusters, then actually you just use 10 centers to represent that class, the whole data set. But usually we talk about dimension reduction, we focus on methods that deal with the columns, variables, how to reduce the number of variables into a few variables that can represent the whole data set. So in this talk, we also focus on this. When I review this method, we focus on the dimension reduction technique that deal with columns, not variables, not clustering. So there are many dimension reduction techniques, and this technique can be classified in different ways. For example, linear, nonlinear, supervised, unsupervised. There was other classification. So linear method, right? There are several. So PCA. So I think all of you are familiar with the PCA. So when we talk about the dimension reduction, the first method we think about it is the principal component analysis. Probabilistic PCA. So this one is similar as PCA. They just use a statistical model to redo PCA in a different way. Essentially, they will give you the same results. Linear discriminant analysis. So this one is also linear, but it's supervised. So LDA is supervised. So they use the response variable, the label, the labeled data. So essentially, say suppose you have a two-dimensional data, right? You find a straight line that can separate two groups. So that line is just the dimension you want. Right? You reduce the two dimension to one dimension. So this linear method do not work well with this pattern, right? nonlinear data. So this is a very famous benchmark problem for dimension reduction. It's called the Swiss law. So it is three dimension. So dimension reduction can be used to unroll this into just a two-dimensional, like a rectangle. Right? This one right now is a curve. Right? So if you can apply dimension reduction, you can get just a two-dimensional representation. So in order to do that, we need a nonlinear method. So there are many nonlinear methods. So the first way to do nonlinear dimension reduction is to just use kernel trick plus some linear method. For example, they have a kernel PCA, so they can detect this nonlinear pattern. Another one is the Laplacian lag map. So this is very close to the spectral clustering. So you have a distance matrix. So distance matrix, this is how you do hierarchical clustering in R, right? You just give the algorithm a distance matrix. That matrix it's a square matrix, so it contains a pairwise distance between all the data points. So once you have that, they can do some matrix operation to get the pattern. So multi-dimensional scaling. So this one also use a distance matrix to do dimension reduction. TSAE, the T distributed stochastic enable embedding. So this method also similar to multi-dimensional scaling, but they do not preserve distance. So multi-dimensional scaling, they preserve the distance because the input is a distance matrix. So they find the MDS find some low dimensional data set such that the pairwise distance match the distance of the original data set. So TSAE does not preserve the distance. So they just give you a low dimension representation, usually 2 dimension. So this method is well popular in medical research because the doctors, they want to visualize some high dimension data. They just use a 2-dimensional figure generated by TSAE. They can print this graph in articles in this research paper because it's 2-dimensional. It's very popular now, this method. So ISO map also related to the MDS and the locally linear embedding, similar to ISO map, but it's faster. So they use the sparse matrix optimization. Auto-encoded. This is a neural network. So neural network can approximate any function, right? So the idea of auto-encoding is to use neural network to approximate the identity function. So the input is high dimension, right? You go to the hidden layer. The hidden layer, you can have a low dimension. So for example, input is 100 dimension. So one hidden layer, say 3 dimension, then use the width of that 3 dimension, you actually get a low dimensional representation of the original data. Then after that, you can go back to the original dimension, decode, encode, then decode. So that's a neural network method. A supervised method, the idea is to extract dimensions that are closely related to the variation of a response variable. So PCA is unsupervised because PCA you only deal with the X data, that means the exponent variable. You do not have a response variable, you do not have Y. But linear discriminant analysis, LDA, they have a label, right? That's Y. So for classification, you have Y. So this is a supervised method. So people also come up supervised PCA. They want to extract the lower dimension that can correspond to a response variable. And then recently, people also develop a supervised TSAE. There are also PCA dimension reduction methods for other data types. For example, the PCA for exponential family data. We know that the exponential family contain other data, right? Including Gaussian distribution for continuous data. They also include the binary, binomial distribution for binary data, and the Poisson distribution for counter data. So PCA for exponential family, they can also deal with just not normal data. The idea is they use some Brueggemann devices to calculate the lower representation, the distance between the lower representation and the original data. And recently, they also developed PCA for compositional data, and the compositional data become more and more popular in actual science and insurance now because of the telematics. So in telematics, we have data like distance traveled, total distance traveled, also distance traveled at different conditions. For example, in urban area, in different places. So if you look at telematic data, you can see some compositional data. So and they also have a lot of zeros. So to deal with this kind of data is also a challenge. And one working paper is to develop exponential family PCA for this compositional data. And if your data has a missing value, people can also use dual PCA, like a probabilistic PCA. And the method proposed in this, so I will talk about it later, is also based on this probabilistic PCA. Now, first, let's look at the standard PCA. So the standard PCA, say X, it's a n times d dimension. So n rows, d columns, so n observations, d variables. Then we want to find a approximation, it's a transpose times v, such that this is the distance is the minimized. So this is a Frobenius norm. So you minimize actually the sum of squares of all the components. So L is the lower dimension. So L usually less than D. So if L equals D, then that is what we do in the standard PCA. We first find the first component by minimizing the maximize the variation. So once we find the first component, then we find the second component, based on some also maximize the variation, but subject to some condition, like the second component is orthogonal to the first. We just extract these components one by one until we get D components. So, but PCA can also formulate as an optimization problem like this. So there are some drawback of the standard PCA because they are algebraic and also like a probabilistic explanation. So for this reason, Tapin and Bishop, they come up with this probabilistic PCA in 1999. And in this method, they can deal with the missing value, as I mentioned before. They use the EM algorithm because they deal with this statistical models. They use the do parameter estimation. They can use EM algorithm. Now let's look at the probabilistic PCA. And so our model, the self-paced probabilistic PCA, is based on this model. So in this PCA, we come up a data model. So X, the observed data X, it can be written by this model. So WZ plus mu plus epsilon. W is a matrix. Z is a latent variable. So we use some Bayesian approach. This is a prior distribution, and epsilon is some noise. So X is some lower dimension data plus this mean, so you can model non-zero mean. So if you center data, then mu is just 0. So this is our model, the data model. So based on the Bayesian approach, so we can estimate all these parameters like W and this parameter sigma. So this is some steps to do the estimation. So the important function is here. So the object function is the log likelihood function. So to estimate this parameters mu, W, and sigma, we have this log likelihood function. So we want to maximize this log likelihood function. This is just like we do in regression. We come up with the log likelihood function, they maximize the function by changing the parameters. So the same idea here. So we change this parameter to maximize this log likelihood function. So that's the probabilistic PCA. Now, to handle data with the outliers, we come up we use this self-paced learning mechanism. So this self-learning mechanism was proposed 10 years ago by Kumar and his co-authors. So the idea is here. We introduce this binary variable Vn. So Vn is 0 or 1. So 1 means it's a clean sample. 0 means it's outlier. Okay, so we just sum this log likelihood function, but we multiply this Vn here. So if Vn is outlier, so actually this term is gone, right? So if it's 1, it's just included. We also subtract this term, is a regularization term. So beta is a hyperparameter. So this is a self-paced learning. So the idea is to learn the easy data points first. Then once you have a learned model, right? Then you deal with the hard data points that are hard to learn. So how to implement that? We do that through this beta and Vn. Okay, beta. Later we'll talk about the algorithm. So beta will change during the process. It's not fixed. So this is the idea. Right? The main idea is to introduce this binary. So this is the algorithm. So we maximize the log function to minimize this negative log function. We minimize this. So this is how the mu is estimated using this optimization. Then we use EM algorithm to minimize this function. So this is getting very complicated. This is each step. This is how we estimate this this variables. So here, this Vn, this binary variable used to determine whether a data point is an outlier or not, right? So if Ln, so Ln is this likelihood function, right, for that data point xn. Right? So if Ln larger than beta, so it's a outlier, right? 0 is outlier. If Ln is less or equal than beta, then it's a clean parameter, right? Because once you fix this parameter and you want to minimize this, so it's very easy. It's an easy optimization problem you can solve analytically. Now this is the algorithm. So the input is the data set, and beta is not an input parameter. Actually, you input another parameter called eta. So beta change every iteration. Okay, so actually we increase beta a little bit in each iteration because you start with a small beta, right? Then you have a lot of outliers at the beginning, right? You have a lot of outliers. So then you have a small subset for clean sample. So you just want to get the model trained, right? Not just arbitrarily. You train the model a little bit. Then after some iteration, you increase beta, like eta. I think in our paper we used 1.01. So each time you increase beta 1%, then eventually your model can deal with all data points. So this is the whole algorithm. Now let me show you some numerical results. So this is a two-dimensional data, right? So this is the clean data, the two-dimensional data. If you apply PCA, PPCA, and self-pasted PPCA, so they give you essentially the same output. Now in the second data set, you have some outliers, right? So if you apply the traditional PCA, it will give you this biased, right? It will not match this majority of the normal data points. PPCA is same, right? Because essentially these two are same, equivalent. The only difference is this one use Laplace function, and this one they just use matrix decomposition. Now this one self-pasted PPCA, they can handle the data well because these outliers are excluded from the computation. There's no impact. So here are some references. So I think I'm going to stop here. So that's yeah. Thank you for attending.